Welcome to e-Pathshala lecture series on computer science. We are discussing on the paper cryptography and network security. The modules what we are going to discuss under this paper is prime numbers, Euler's and Fermat theorem. The objective of this particular topic is we are going to introduce the prime number and also the importance of prime number in the field of cryptography, and we are going to discuss about Euler's and Fermat theorem and various examples related with Fermat theorems and Euler's theorem. And finally, we are going to discuss about Chinese remainder theorem and its application in cryptography. So basically, there will be three groups of positive integers. When I take a positive integer, I have number 1, primes and composite. Number 1 is exactly 1 divisor, that is your 1, and primes exactly 2 divisor, and composite number we have more than 2 divisor. So what is the importance of this prime number is, when I am going to do a process with an encryption or decryption, basically in the case of our cryptography, as in the case of your asymmetric cryptography, where the prime numbers are going to play a very important role. So we want to understand what is a prime number and also how to choose a particular prime number in such a way that we can do a encryption and a decryption. So what is a prime number? A prime is divisible only by itself and 1. So whichever the number if you are going to take, if it is going to be divided by 1 and itself, then we can say that is going to be a prime number. So what is the smallest prime? Example, let us take with respect to a prime number. What is the smallest prime? The smallest prime is 2, which is divisible by 2 and itself. And suppose if I want to take n as any number, for example, if I am going to take n is equal to 10, you are asked to find out the list the prime number smaller than n. That means here the primes smaller than 10. So there are 4 primes less than 10, that is 2, 3, 5 and 7. So what is the interesting thing related with that particular prime number is, the percentage of prime numbers in the range 1 to 10 is 40%, and this percentage will be decreases as the range of the numbers are going to be increases. Suppose if I want to know the cardinality of prime, cardinality whether I say it is going to be a finite or infinite. Suppose I am taking a particular set of values, if I want to say that what is the cardinality of prime numbers if a particular n is given, then we can able to identify with the help of phi of n. In the previous example, let us take this prime number smaller than 10, where n is equal to 10, phi of n. If I take phi of n, I will get 2, 3, 5 and 7. That means phi of n is equal to 4. So similarly, if I want to take a cardinality, the cardinality is the number of prime numbers of given n. So either it is going to be a finite or infinite, that question may arise in our mind. So if I take a prime numbers, that is going to say that there will be a infinite number of primes. For example, if I say the number of primes, if I want to find out for n, then how can I find out? That is given by 2 different formulas with the help of Gaussian and Lagrange's, where they defined, if I want to find the upper limit or the lower limit, suppose I want to find out how many primes are available for 10,000, n is equal to 10,000, so how many prime numbers are less than 10,000, then I can use this particular formula, I can able to find out what is the value of n. So how it is given, n divided by log n less than phi of n less than n log n minus 1.083. This is defined by Gauss and this is defined by Lagrange's. So I can able to define, if n is given, I can able to find out what is the upper limit and the lower limit. Then I can define how many prime numbers are going to be there. Let us see this example, how I am saying there will be infinite prime numbers, because the reason is, if I take a set of values, okay, only primes are in the set 2, 3, 5, 7, 11, 13, 17. If I am taking a particular prime number p 510, 510, then p plus 1 is 510, 511, then when I say that, I can able to factorize this into 19 into 97 into 277, where 19, 97, 277 not in this particular set, because we have set with the prime numbers of up to 17. So 19, 97, 277, all these are not in the set, then I can say that you are going to have a infinite number of primes. Okay, we cannot able to, so that is what here is given. So when I am going to say that when any number, if it is going to be dividing p plus 1 which is not in the set, then we can say that it is going to be infinite number of prime. And similarly, finding the cardinality, suppose I want the cardinality of primes, I want to find out the cardinality of prime. So given an example here, for the number primes less than, suppose I am taking 10 lakhs, right. So that is going to be how many prime numbers are going to be where the n value is given as 10 lakhs, right. So if I am taking that, the approximate range is 72,383 to 78,543. How we got exactly this value is by applying this particular equation. So when I am taking this n as 10 lakhs, so n 10 lakhs divided by log n, I will get this 72,383, and similarly using this Lagrange's, when I am going to say that n is 10 lakhs, log n minus 1.8366, then I will getting 78,543. So this is the way how we can able to say exactly how many prime numbers are available for the given number of n. The actual number of prime is actually how many prime numbers are less than 10 lakh is 78,498. So approximately using this expression we can able to get the particular number of prime number. Next, suppose a number is given, we want to say whether the given number is prime or not. How I am going to determine that? So if a number is given, let us take n, how we can say whether the given number is prime? Why we are talking about checking for the prime numbers is because when I am going for using key generation process in RSA, that is your asymmetric cryptography, we want to use a largest prime number. Suppose I am going for largest prime number, I can't choose any n value, specifically I want to check with whether this is going to be suitable for generating the key. In such a manner, if n is given, I have to verify an algorithm to verify that whether it is going to be a prime number or not. So the answer is that we need to see if the number is divisible by all prime that is less than. It is very simple method. What we can do is, okay, I am going to take the, for example, I want to take 100, square root of 100, I will get 10. I will take all the prime number which is less than 10, then I will started to dividing that number, I will see whether it is divisible or not. If it is not divisible, I say that it is going to be a prime number. But actually this may be very simple method, but it is not a efficient method according to our algorithm. So the time complexity, that also the efficiency will be measured with respect to this method. It is very difficult to find out if the number is going to be very large n, okay, n value is going to be very large. So we will see some of the example related to the prime. Is 97 is a prime? I want to say is a 97 a prime. So according to this we have to find out the square root of that. So square root of 97 is 9. So the prime less than 9 are 2, 3, 5 and 7. So we need to see that if 97 is divisible by any of these numbers. Suppose I want to check whether 2 is divisible dividing 97, 3 is dividing 97, 5 is dividing. So no number which is less than 9 is not going to divide the 97. So I can say it is not, so n 97 is a prime number. Similarly, if another value, if I take n is equal to 301, I want to check whether 301 is a prime number. What I will do is I will take a square root of 301 where I am getting 17. So I will take all the values which are less than 17 as a prime numbers, 2, 3, 5, 7, 11, 13 and 17. Then the number 2, 3 and 5 do not divide 301 but 7 divides. So therefore 301 is not a prime number. So what we have to do is, this method is not going to help you for very large number. The next concept what we are going to discuss related with the cryptography is Euler's phi function, or we call this Euler's totem function. So this is going to play a very important role in cryptography, because where you using a cryptographic algorithm, whenever I am going for an asymmetric cryptography, I want to use this particular function phi of n. Phi of n, if I am able to find out, then only I can able to compute the key during the encryption process as well as decryption process. So, it is very important function where it is defined by this Euler's phi function. So, what is this phi of n? Suppose I am going to say that what is the value of phi of 13? So, if I want to say phi of n, n can be any number. If I want to say what is the phi of n, then I have to follow these 4 rules. So, what is the first rule says, if n is equal to 1, then I can directly say that phi of 1 is 0. If phi of p is nothing but if I am choosing n value, the n is a prime number, then directly I can say phi of p is p minus 1. That is, whenever you have a n value as a prime number, directly we can say that phi of n is p minus 1. Then if it is going to be a multiple of m into n, where m and n are relatively prime. You know what is relatively prime? Yes, we already know, because m and n are relative prime means if I am finding the GCD of m comma n, then I will get 1. Then I say it is relatively prime or co-prime. So, if I am getting a multiple of a relatively prime number, then we can do that separately, phi of m into phi of n. So, phi of m, if it is a prime number, directly we can able to do with the help of p minus 1, or again we go for finding that it is going to be m cross n, then I will say that phi of m into phi of n. So, like that I can able to repeatedly do that, then I will able to find out what is the phi of n value. Phi of p power e, that is where p power any value, that is any integer, then I can say it is a factorized number. If it is going to be a factorized number, then I say p power e minus p power e minus 1 if p is a prime. So, based on these 4 rules only we can able to find out the value for phi of n. So, when I want to get, for example, 10, what is the phi of n of 10? Suppose I am taking 10, then I have to consider 10 can be given by 2 into 5, 2 into 5, 2 into 5 which is comes under the rule of 3. So, 10 we can represent by 2 into 5, that is phi of 2 into phi of 5. So, phi of 2, again 2 is a prime number, I say I apply the second rule, I will get phi of 2 is 1, because 2 minus 1 will get 1. Similarly, I go for phi of 5, where 5 is a prime number, then I apply the second rule, I will get 4. So, 1 into 4 I will get the answer as phi of 10 is equal to 4. That is what Euler's phi function. So, what is the important thing we have to understand is, we need to remember these rules when before you are going to apply for finding any phi of n. So, suppose I have a combination of above this, right. Suppose I am having a value phi of n which is having combining above 4 rules, then it can be given as an example where it is can be factorized. N is equal to p1 e power 1 into p2 e power 2, like that pk e power k. So, what I can do is I can combine the third and fourth rule, I want to find out similarly what I did for the 10. When I am taking 10, I can represent by 2 power 1 into 5 power 1, like that also we can able to say, right. So, 2 power 1 into 5 power 1, so I will say that I can able to apply phi of n p power e minus e1 minus p power e minus 1. Similarly, pi of 2 into p2 power e2 minus p2 e2 minus 1, like that we can able to see the difficulty of finding depends upon the difficulty of factorization of the n value. That is the only thing we need to do. So, if you are able to do a factorization of n value, easily we can able to find out the phi of n. Okay, let us see some of the examples related to the Euler's dotted function or Euler's phi function. Here, what is the value of phi of 13? So, as we know 13 is a prime, directly applying the second rule, that is phi of 13 is equal to 13 minus 1, that is 12. Then similarly, what is the value of 10? Already we have computed. We can able to see that the third rule, according to the third rule, 10 can be written as phi of 2 into phi of 5, So, that is 1 into 4, I will get answer is equal to 4. So, because 2 and 5 are prime numbers. Similarly, if I want to go for taking another value whose 240, if I am taking 240, 240 can be represented by p power e minus 1, p1 power e1, p2 power e1, p3 power e1. So, I am taking the prime numbers factorization, as what we mentioned, the difficulty of finding the phi of n is purely depends upon how we are going to factorize the number n. So, now we have factorized the number as 240 can be factorized as with the respect to p power e. So, p power e it is taken 2 power 4. So, by taking the combined rule as what this slide which is explaining about the combine of third and fourth rule, we can able to say that p1 power e1 minus p1 power e minus 1. So, that is what they are mentioned in this particular point, where you can say that phi of 240 is equal to p1 that is 2, this one 2 power e1 that is 4 minus p1 power e1 minus 1 that is 3. Similarly, if you take the next value p2 e power 1 minus p2 e2 minus 1. Similarly, p3 e power 3 minus p3 power e3 minus 1. So, we are getting 2 power 4 minus 2 power 3, 3 power 1 minus 3 power 3, 3 power 0, 5 power 1 minus 5 power 0. So, when I am going to simplify that, I will get 64. Similarly, when I go for 49, where it is going to be a square of a number. So, this is you cannot take directly like it is going to be multiple of 7 into 7. Instead of that, what you have to do is we have to take the square of the number. As we can say that when 49 is given, phi of 7 into phi of 7 that is 6 into 6, you cannot say 36, because no, the third rules apply when m and n are relatively prime. Why we cannot apply this is because the reason is 7 and 7s are not relatively prime numbers. We have to take 49 is equal to that is 7 square. So, we need to use the fourth rule. So, fourth rule as per p power e, then you can say that p power e1 minus p power e1 minus 1 like that. So, 7 square minus 7 power 1 that is 42, 49 minus 7 will get 42. So, we can say that the Euler rotating function for 49 is not 36, it is 42. Why? Because whenever you are going to apply a particular rule, we have to know these two must be, if I am applying third rule, I should ensure that whether it is going to be relatively prime or not. Okay. Now, according to our Euler rotating function, we say that, right, how many values are going to be there, but what are the values, right? That is what it is given is an example. What is the number of element in the Z14? Okay, it is saying that in the particular group, okay, when I am going to take this particular where I have a group, in this group how many elements are there with the help of Euler's rotating function. So, how I am going to get this? Phi of 14 is equal to, we can able to say that 14 is multiple of 7 into 2, both are prime numbers. 7 is a prime number, 2 is a prime number. So, 7 when I am going to apply directly, I can apply the second rule. When I apply the second rule, I will get 6 and 1, that is equal to 6. So, what are the elements? We say that 1, 3, 5, 9, 11 and 13. So, what are these numbers? These numbers are relatively prime with 14. If I take this number, okay, and 3 if I take, then I will get GCD of 3 comma 14, I will get 1. Then I take 5, I will get 5, GCD of 5 comma 14, I will get 1. So, this actually, what is the purpose of this Euler rotating function is, it will give the number of element which are relatively prime to particular group of 14. So, as what we can able to see that the number of elements which is going to be relatively prime with 14, that is with the help of Euler rotating function we got 6, and what are the elements we have to find out. So, we say 1, 3, 5, 9, 11 and 13. The interesting point is, if n is greater than 2, the value of phi of n is always will get even. Okay. Next theorem we are going to discuss about Fermat's Little theorem. There are two versions of Fermat's Little theorem. Okay, what is the application of Fermat's Little theorem is in the last session where we discussed about modular exponentiation. So this Fermat's and another one next theorem what we have is Euler's theorem. Both will help you to find out faster and quickly and very easily to find out the modular exponentiation for large integer, large power integer. So here the Fermat Little theorem states that if p is a prime and a is an integer such that p does not divide a. So what is the statement is, I have to consider before I am going to apply this theorem, I have to verify whether the number, suppose I am taking p is a, here p is a modulus, right. So p is a modulus, then that must be a prime number and a what I am going to choose. So is such that p does not divide the a. So if I take a when I am going to take divide by p, then it does not divide the p by. So p does not divide a, then I can say that a power p minus 1 is congruent to 1 mod p, congruent to 1 mod p. So what I am saying here, whenever I have a modular exponentiation in such a way that if I have a modulo of prime number and any integer, then if array such that a power p minus 1, then I can directly say that is equal to 1. I do not want to do for, because in the last session when we are discussing about modular exponentiation, we use the square and multiplication method or fast exponentiation method. Those are more time consuming. So most of the cases whenever you are going for a modular exponentiation, you want to solve the modular exponentiation for very large integer, we can get use of these theorems. The second version, which is removing the condition. What is the condition? P does not divide a, that condition is removed. So what is this theorem says? A power p, where a is an integer, p is a prime number, is congruent to a mod p. So when I am taking a mod p, if I am getting a, okay, when I am saying that a power mod p, then I directly say that the answer is a. I do not want to solve this, right. Find the result of 6 power 10 mod 11, right. According to the Fermat theorem, we say that p is prime and a is an integer, p does not divide a. So we will see that which version is suitable for this example. Suppose I am taking, okay, p is 11, that is a prime number, good. Then we say a is 6. So here what is the condition says? P does not divide a. Here p is not dividing a, then we can apply the first version of Fermat Little theorem, then we can get the answer as 1. We do not want to solve it, directly you can write the answer is 1. So this is the first version of Fermat's Little theorem, where p is a 11 and 6 is not divided by p, that is your 11, then I can say the answer is 1. I do not want to go for simplifying as what we did in the last session. Similarly, if I go for finding the result of 3 power 12 mod 11, now we can able to see that here where I take this again the same thing, here the exponent is 12 and the modulus is 11, which are not same. So as what we can able to see that here what they are saying, these are not same, right. Then we cannot directly we cannot apply the first version. So what we do is we substitute this with the solving of Fermat Little theorem. So what we are doing, we will take 3 power 12 mod 11, that is according to our property of exponentiation arithmetic, then we can write 3 power 11 into 3 mod 11, 3 power 11 mod 11, 3 mod 11. 3 power 11 mod 11 is nothing but, here we can take the second version of your Fermat theorem. So a power 11 congruent to a mod 11. So what is the a here? A is 3, we are writing directly 3, and 3 mod 11, the remainder is 3. So 3 into 3 we get 9, mod 11 is equal to 9. So this case is different. The previous case is directly applying the first version. One condition we have to verify whether it is divisible or not. The second version is it is removing the condition. It is not a problem with dividing or not, but the thing is we have to make this a power p mod p. Another application of Fermat-Little theorem is multiplicative inverse. When you are computing multiplicative inverse, in the last session we used extended Euclidean algorithm, where it is provided very iterative steps and also most time consuming to compute a very large inverse prime number. It will be more steps are involved. Instead of that, when I am going to apply the Fermat's theorem, if this is going to satisfying the property of Fermat's theorem, very basically you can able to solve the inverse multiplication. Why we want to study about inverse multiplication? As you know very well, whenever your encryption process is going to be happening, your decryption process is going to be inverse of encryption process. So, wherever I do, definitely I have to go for inverse of that also. So, when I am doing a multiplicative inverse, always I will say a power a inverse mod p. I say that a inverse mod p. So, how I can give that is a power p minus 2 mod p. So, I can state this whenever I have a prime number as a modulus, if I want to find an inverse, instead of finding an inverse, directly I can apply the Fermat theorem. I say that a power p minus 2 mod p. So, what is happening? I am removing this inverse, I am getting the exponentiation. Once I am getting an exponentiation, then it is easy for me to solve it with the Fermat's theorem. As what we can able to see, some of the examples are given where the prime numbers without using the extended Euclidean algorithm. We are not going to use the extended Euclidean algorithm, directly we can able to get it with the help of Fermat's theorem. For example, if this is 8 inverse mod 17, that is equal to 8, that is according to this inverse property 8 power p. What is the p? 17 minus 2 mod 17. So, I am getting 8 power 15 mod 17, then I can able to solve it according to the Fermat's theorem, or I can able to solve it with the modular exponentiation. Similarly, for the other example also we can able to solve it 5 inverse mod 23, 60 inverse mod 101, like that we can able to solve it. Next theorem is Euler's theorem. The first version says that if n and a are co-prime, that is co-prime or relatively prime positive integer, then I can say that a power phi of n. What is this phi of n? It is a Euler's totet function. That is a important why we studied Euler totet function in the beginning of the session. Is congruent to 1 mod n. So, it is removing the condition of your Fermat. It is not worrying about whether it is a prime number or not, any integer n. Similarly, the second version we can say that it is not considering a and r must be a co-prime, simply it can be any integer. We say that a power k into phi of n plus 1 is congruent to a mod n. So, here you can able to see that a power k is an integer, any integer, into phi of n, that is your Euler's totet function, plus 1 is equal to a mod n. So, the second version of theorem is used, actually this version we used in the RSA. RSA is a symmetric cryptographic function. Let us say one example related with that. 6 power 24 mod 35, according to the first version we can directly say that 24 is phi of 35, we will get 1. Similarly, go for the second example, which is not in the first version, we will use the second version, we will get, here we consider k is equal to 1, then we can able to simplify that phi of 77 plus 1, because phi of 77 is 62, 60, actually this is a 61 plus 1 we will get 62. So, 20 into 20 mod 77 will get the 15. So, this is the application similar to that of your Fermat, but here what is the condition is we are not worrying whether is a modulo is a prime or not. So, without checking of this primeness we can able to use any integer, but the condition is we should get the Euler totet function to ensure that a power is a phi of n. Similarly, this case also it is not checking for the co-prime, simply it says that a power k into phi of n plus 1 we can able to. Similarly, it is also used for finding the multiplicative inverse. Here the condition is inverse mod n can be represented by a phi of n minus 1, that is mod n, a phi of n minus 1 mod n. So, same example where you can able to represent a 8 power phi of 77 minus 1, that is 8 power 59 mod 77, either you can use first version or second version. we can able to simplify to get that answer as 29 mod 77. Similarly, for 7 inverse mod 15, 13 mod 15, we are applying the inverse property of your Euler's theorem. So, these two theorems were important in the cryptography. The overall in today's session we have discussed the importance of prime numbers and their application in the field of cryptography, and also we have discussed two theorems, Euler's and Fermat theorem, and also we worked with the various examples related with the Euler's and Fermat theorems. Thank you.